pleasure to it's my pleasure to introduce Marina Poulet from Institut Grenoble. She will speak about Zariski-dense subgroups of Galois group for Mahler equation. Marina, please.
Thank you for the invitation. So I will present to you an analog of the Schlesinger density theorem for Mahler equation, that is Zariski-dense subgroups of Galois groups for Mahler equation. So first, I will present the Schlesinger theorem, which is a theorem in differential Galois theory. So I remind you that in classical Galois theory, we are interested in complex roots of polynomials with rational coefficients. And the idea of Galois was to look at the permutations of the roots of this polynomial, which preserve the algebraic relations between these roots. And he praised the idea that this idea can be transposed to other contexts, such as functional equations. And then many years later, Picard and Vessieux developed a theory for linear differential equations, so called the Picard-Vessieux theory, or also called the differential Galois theory. So first, I will talk about the differential Galois theory. And in differential Galois theory, we are looking at linear differential equations, and also we can put it as a differential system like this. And we know from Cauchy's theorem that if Z0 is not a pole of A, then there exists a fundamental matrix of solutions of this system. That is, it is an invertible matrix whose entries are function analytic around Z0, and such that it is a solution of this system. So now we know a fundamental matrix of solution. We can consider the smallest field containing the Barth field, which is here the field of rational functions, and also all the entries of the matrix Y. So I will denote it this field K like this. So it is the smallest field containing the field of rational function and all the entries of the fundamental matrix of solutions. And this field K is, with the derivation, the usual derivation, is called the Picard-Vessieux field for this system. And by definition, the differential Galois group is the group of automorphism of K, which is the identity on the field of rational functions and which commutes with the derivation. So let us do the analogy between the classic case. So in the classic case, as I told you before, we are looking at polynomials and the roots of this polynomial. Here, instead of looking at this, we are looking at differential systems and fundamental matrix of solutions. And the Picard-Vessieux field is the field which plays the roles of the splitting field in the classical case. And then we have, in the same way, the differential Galois group, which is the automorphism of K, which are the identity on the field of rational functions, and which commutes with the derivation. So here we have a supplementary condition, which is this condition in blue. And in fact, this condition is quite natural because it ensures that if you take an element of the differential Galois group and a fundamental matrix of solution Y, then sigma Y is also a fundamental matrix of solutions. And in order to see this, you can do this computation. So you take the derivative of sigma Y, you use the fact that it commutes with the derivation, and then you remember that sigma fix the matrix A because it is the identity on the field of rational functions. And so you can see like that sigma Y is also a fundamental matrix of solutions. So here there is the analogy between the differential case and the classical case, but of course there are a lot of difference between these two theories, and the fundamental difference is that in the classical case, the Galois group is finite because it is a subgroup of the group of permutations of the roots of the polynomial, but in the differential case, it is in general infinite. So it is only finite in some cases. So in general, it is an infinite group, and we see that we can see that it satisfies fundamental property, which is this one. So you take an element of the differential Galois group, sigma, and you associate to it this matrix, C sigma, and it gives you a faithful representation of this differential Galois group. And we write G-Gale, the image of this representation, so you can identify the differential Galois group with G-Gale. And the fundamental property of the differential Galois group is that it is an algebraic subgroup of GLN of C. So it is defined by polynomial equations, and it is a subgroup of GLN of C. So just one remark about this theorem: the fact that C sigma is a constant matrix, it is invertible by construction, and it is a constant matrix because when you take the derivative, you apply the classical rules, and then you see that equal to 0. So C sigma is a constant matrix. And in general, if you take two fundamental matrices of solutions of the same differential system, denoted by y1 and y2, then when you consider such product, you will have a constant matrix, an invertible constant matrix, doing the same computation as before. So we have this property of the differential Galois group, that we can identify it with an algebraic subgroup of GLN of C. And now we want to find a Zariski-dense subgroup in this group. And the idea was to consider a notion coming from the analysis called the monodromy. So I introduce now the monodromy. So first we consider the set of singularities of the differential system. We say that a point is a singularity of the system if it is a pole of the matrix A. We also say that the point infinity is a singularity of the system if when you do the change of variables t equal 1 over z, the point t equals 0 is the singularity of the system. So we consider the set of singularities, and then you take a point which is not a singularity, and you consider a continuous path avoiding such singularities, which become at this nut and which end at the nut. Okay. And what we do now is that we do an analytic continuation of the entries of the fundamental matrix of solution Y along this path. And this gives us a matrix denoted by gamma Y. So just recall how we can do analytic continuation. So you take, for example, the logarithm in a neighborhood of 1, 2.1, and then you consider another open which intersects with the previous one, and you consider the only function defined on the second open set, which is equal to the logarithm defined of the first open set. Okay, so you do this for all open which recover the unit cycle, and then like this you do the analytic continuation of the logarithm around the unit circle. Okay, and at the end we see that we obtain the logarithm plus 2i pi. And at the end, so we don't have the same function that we had at the beginning. It is because the logarithm is not analytic at 0. And if instead of taking the logarithm, you take a function which is meromorphic on a domain containing the unit cycle, then at the end of this process, you will have the same function. So this measures the lack of analyticity of the function on the domain you consider. And you do this kind of analytic continuation to the entries of the matrix Y, and we denote it by gamma Y, the matrix we have at the end. And this matrix, gamma Y, is the solution of the previous differential system. So as I told you before, because you have two solutions of the same differential system, They differ by a constant matrix denoted here n gamma. And thanks to this matrix n gamma, which is a constant and invertible matrix, we can consider the monodromy representation. And the monodromy representation is this one, which associates to class gamma the matrix n gamma. And we can see that n gamma does not depend on the homotopy class of gamma. So this is well defined like this. And by definition, the monodromy group will be the image of this representation. We always ask that the monodromy group is included in the Galois group. In fact, is in most of cases strictly included inside it. But we can know something else about this monodromy group, and this is the Schlesinger theorem, which told us that if the system is regular singular, then this monodromy group is Zariski-dense in the Galois group. And the only hypothesis of this theorem is the regular singularity. And this means that the system you consider must have solutions of moderate growth around on such sectors centered at the singularities of the system. So it's just to ensure that the matrix Y at the beginning, the matrix of fundamental matrix of solutions, as entries would have moderate growth on such sectors. So with this hypothesis, we have that the monodromy group is Zariski-dense in the Galois group. If we get rid of this hypothesis, it is not anymore true, this theorem, but there is a theorem of Ramis, which told us that if you don't consider that the system is regular singular, then if you add to the monodromy the Stokes matrices and the exponential torus, then you also obtain a group which is Zariski-dense in the Galois group. So you have to add something else. It is not sufficient only with the monodromy.
I have questions. Okay?
Yes.
All right. So here, do you want to know generally that a particular group is a Zariski-dense, or you just have a Galois group and you want to find a Zariski-dense subgroup? So which direction is this you're thinking about?
So we have a Galois group and we want to know a Zariski-dense subgroup in this Galois group, or we can construct it.
So you want to find all of them, or yeah? So I'm not exactly sure.
No, not all Zariski-dense subgroups.
Yes. So what is the like overall problem? Find a Zariski-dense subgroup, or find all of them? Describe them in some way.
No. Just find one Zariski-dense subgroup, and it can give you information about the Galois group. Sometimes, in fact, this kind of theorem can be used to compute some Galois groups, because you know the Zariski-dense subgroups thanks to the monodromy, and then it can help you to compute the Galois group.
Mm-hmm. But knowing that a group, representing this group as the Zariski closure of a subgroup, is it not sufficient to say that you already computed it?
Sorry, I don't understand the question.
Suppose you found a Zariski-dense subgroup.
Yes.
Just so having found that, aren't you finished with computing the group?
Once I finish to compute the Zariski-dense subgroup?
Once you found the Zariski-dense subgroup, what is else to do to compute the group? Isn't a sufficient representation of the group as a Zariski-dense subgroup?
I think that if you know Zariski-dense subgroup, then if you can compute it, then you will have your Galois group.
Yes, that's it. So that's okay. Got it. Thank you.
Okay.
And I have a second question. So this is about the differential equation with not specified initial conditions, correct?
Yes.
Initial conditions. What about if you specify initial conditions? How does it work?
When you put an initial condition like
Yes.
y0 equals something.
Yes.
So since at the beginning you don't need a special condition at the point 0 or another point, I don't think that it is a problem. You can apply the same theory.
So I couldn't hear, the voice was breaking. Could you repeat that?
At the beginning, we don't assume a special condition more than that the matrix has entries in rational functions. And in fact, you can generalize it to other bases, but here we consider only rational functions, and it is the only condition. So if you had a condition like you specified y0 equals something, you will have this kind of the same result because we don't specify that the matrix Y equals something at a point.
Mm-hmm.
Okay.
Thank you.
Okay. And in fact, for the question about computation, they use this theorem to compute Galois group for hypergeometric equations, for example. So they compute the monodromy group for hypergeometric equations, and then thanks to this theorem, you can have the Galois group. Okay.
Very nice. Thank you.
Thank you. So we have an analog of this Schrödinger theorem, but for two different systems. And two different systems is a system of this form. So you take Q to be a complex number whose modulus is greater than 1. And then you consider the operator sigma Q like this. And here the Q different system is a system of this form. And instead of looking at the singularities of this system, as we did in the differential case, here we are looking at the fixed point of sigma q. So the point 0 and infinite. And an analog of the Schrödinger density theorem was first obtained for two different systems with systems which are said to be regular. And a regular Q-different system is a particular case of a singular regular Q-different system. So first I will talk about the case of regular Q-different systems. So we say that a system of this form is regular if for these two fixed points of the operator sigma q, the entries of the matrix A are analytic function at this point, and it is the identity at this point also. So it is a regular system, and it is a special case of regular singular systems. And an analog of Schrödinger theorem for regular Q-different systems was first obtained by Ettinghoff. And the idea of Ettinghoff were the following. So first, we construct a fundamental matrix of solutions at the point 0. We denoted by Y0 this fundamental matrix of solutions. And it has entries which are analytic functions at the point 0. And thanks to this and the fact that it is a solution, so it satisfies this equality here, we can see in fact that this matrix Y0, its entries are meromorphic functions on the context plane. So these entries are analytic functions at 0, and thanks to sigma q, we can extend it as a meromorphic function on all the context plane. And similarly, it does the same thing for the point infinity, and here we have a fundamental matrix of solutions whose entries are meromorphic functions of P1C privated minus 0. And then we consider a connection matrix of Birkhoff like this. And it is the KID of Ettinghoff to consider such matrix. It is the product like this of the two previous fundamental matrix of solutions. Its entries are meromorphic function on C star, and it satisfies this equality here, that is, it is invariant under the operator sigma q. And it is like before, we have seen for differential systems that such a product is a constant matrix. In the case of Q-different systems, such product is a matrix invariant by the operator sigma q with the same kind of computations. And this connection matrix of Birkhoff plays the role of the monodromy in the case of Q-different systems. And in fact, Ettinghoff proves that if you consider the group G beer, which is a subgroup of GLN of C generated by these products, for all V and W which are not a singularity of P. That is the point at which you can evaluate the matrix P and at which P is also invertible. And if you consider this group, Ettinghoff proves that this group is Zariski-dense in the Galois group, in the different Galois group. And he also proves that, in fact, G beer is closed, so you have this equality of groups. So in the case of Q-different systems, the connection matrix plays the role of the monodromy for the differential case. And you have, like this, a Zariski-dense subgroup of the Galois group. And in fact, it's equal because it is closed. And then this result was also extended to singular regular Q-different systems thanks to two methods. The first, you have a method by Van der Poot and Singer, and they use Picard-Vessios theory, as I explained before, but applied to different systems. And they use symbols to apply this Picard-Vessios theory. And another approach was the one of Solois, who used Tanakian categories. So I have no time to explain in detail these two methods, but just let me told you that these two methods exist, and they give us an analog of the Schlesinger theorem for singular regular Q-different systems. So now I will explain you how we can extend this to Mahler systems. So from many years now, Mahler systems are systems which are well studied because of the link with automata theory. So since the time we discovered that there is a link between Mahler systems and automata theory, it became a really active research topic. And this is why we are interested in this kind of system. So it's interesting to have such a density theorem for Mahler systems. And the idea was to look at, so a Mahler system is a system of this form. So instead of taking the operator sigma q, here you take the operator Cp, which is this operator. We see where C is an integer greater than 1. And first, I will explain you the regular case, which is the simplest case, the easier one. First, we assume, as in the case of Q-different systems, that the matrix A is the identity on the point 0 and infinity, which are also two fixed points of Cp. And so we construct a fundamental matrix of solution at 0. It has also analytic function here for its entries. And here the operator Cp does not allow you to have entries meromorphic on all the context planes. the operator CP allows you only to have entries which are meromorphic function on the unit list. And similarly, at the point infinity, the fundamental matrix of solution as its entries are meromorphic function on the complementary of the closed unit list. So here there is a difference between Mahler's case and the Q-difference case. You do not have something which is meromorphic on C and the complementary of 0. You have something meromorphic on the unit disk and the complementary of the closed unit disk. And so here we want to consider this product as previously, but we can't, because they are defined on two disjoint domains, so you can consider this product. And moreover, from Rande's theorem, we know that the unit cycle is a natural boundary for this solution. That is, the matrix Y0, its entries are meromorphic function on the unit disk, and all the points of the singular on the unit circle are essential singularities, or if there is only one point in the unit circle which is not a singularity of Y0, it means that the matrix Y0, its entries are rational functions. So you have a natural boundary in this sense. You cannot go after the unit cycle. If you are inside, or if you can go outside, it is because, in fact, you have rational functions. So the case not interesting. So we cannot, and the idea was to consider the point 1, because it is also a fixed point of this operator. And then instead of having only one connection matrix, we can consider two connection matrices. These two matrices here. And so we have to construct a fundamental matrix of solution at the point 1. In order to do that, so we assume now that the matrix A is the identity at the point 1 also. In order to construct a fundamental matrix of solutions at the point 1, you can do the following thing. So you take your Mahler system at the point 1, and then you do this change of variables. You do this change of variables, and then you see that at the end you have a Q-different system. In fact, a P-different system. And then you want to come back to the previous Mahler system, and here we use this logarithm defined on the universal cover of C star. For example, that the universal cover of the star is this set, and this logarithm is defined like that. And now you know that we know a fundamental matrix of solution of this Q-different system, and as we have seen before, this matrix of solution, its entries are meromorphic function on all the complex planes. When you do the composition with this logarithm, which is the holomorphic function, you get a solution of the previous Mahler system, which is meromorphic on all the universal cover of C star. So like this, we have this proposition, which gives you a matrix denoted by Y1 tilde, which is meromorphic on all the universal cover of C star. And in the following, I will denote by pi the exponential composed with this logarithm. I denote it by pi because it is a projection. You can, if you do the computation, you see that it is a projection of an element here to the point R, to the first component of this couple. And then if we take a point of this universal cover of C star, then we denote by P star omega, P star W, the matrix W composed with pi. Okay, so it is notations for the rest of the talk. And then, so we have this fundamental matrix of solution at the point 1, and we already know two fundamental matrices of solution at the point 0 and infinity. And so we can consider these two connection matrices. The first one is the link between 0 and 1, and the second one is the link between the infinity and 1. Okay? And by construction, the first one, its entries are meromorphic function on sigma 0, which is a part of the universal cover of C star, which is sent by pi to the unit disk. Okay, and sigma infinity is a part also of the universal cover of C star, sent by pi projection on the complementary of the closed unity. So you have these two connection matrices, and also we have that they satisfy this equality. It is invariant in the operator CC. So the idea, in order to have an analog of the Schrödinger density theorem for this kind of equation, I use the Tannakian approach. So I use Tannakian categories. So I just recall some facts about Tannakian categories. So Tannakian categories, you just have to know that it is a category which with a tensor product. Okay, it is with a tensor product, and also with a fiber functor denoted by omega. So just recall that it is a category with a tensor product and a fiber functor denoted by omega, which is a functor from this category to the category of finite dimensional vector space over C. And by definition, the Galois group of a Tannakian category is the automorphism, the tensor automorphism of this fiber functor. And here in the Mahler case, so we want to consider Tannakian categories. The first one we are interested in is the category of regular Mahler systems. So the objects of this category are all regular systems, and we also take all the Mahler systems which are equivalent to a regular one, and morphisms are defined like this. Okay, so we don't need it for after, so I don't insist on it. And then we also consider the category of connections denoted by C. The objects of this category are the two connection matrices constructed before. So they satisfy the first point, as I said previously. And also you have to assume that there exists a matrix denoted by W1 tilde, such that it satisfies this system. And you have to think that this matrix W1 tilde is the matrix Y1 tilde constructed before. And this matrix W0 and W infinity is the two previous fundamental matrices constructed at the point 0 and infinity. So it is just as before for this object. And then morphisms are these three matrices, which are constant matrices and satisfying this equality. And we can prove that there are equivalent categories and there are Tannakian categories. The category of connection is a Tannakian category with this tensor product on matrices and with these fiber functors. So we consider three fiber functors, and they send an object of this category to this vector space, where n is the size of the matrices inside this object. You know, this object is two connection matrices. They have the same size as the matrix at the beginning, which is called n, denoted by n. And then this fiber functors send this morphism to the associate morphism, which is constant matrices So it is a morphism of finite dimensional vector space. Okay. So this is a Tanaka category with these two facts. And as I said previously, the Galois group is this one. And we want to construct elements of the Galois group. In order to construct elements of this Galois group, we want first to construct isomorphism from omega 0 to omega 1. And then when we compose such isomorphism, we get elements in the Galois group. So I recall the definition of an isomorphism from omega 0 to omega 1. And such an isomorphism is a family denoted by eta x, which are invertible. And they have to satisfy these two conditions. The first one is to be a morphism of commutator. So this family must be like this. This diagram must commute. So you have to construct eta x1 and eta x2, such as for all objects of this category x1, x2, this diagram commutes. And then you have a condition of tensor compatibility. Okay. So let us just see that this one is indeed an isomorphism from omega 0 to omega 1. The first condition comes from the fact that this diagram commutes, and it is because in the category of connection, by construction, S1 times m tilde 0 equal m tilde 0 times S0. So then you apply it to the point R tilde, and so this diagram commutes. It is by construction. And moreover, m tilde 0 is invertible at the point 1, at the point A tilde, sorry. It is because I choose A tilde not to be a singularity of this matrix. So by construction, it is an invertible matrix. And the tensor compatibility is immediate because you have this equality. When you evaluate the tensor product, it's like if you evaluate each matrix and then you do the tensor product. So, okay, we have these elements which are isomorphism from omega 0 to omega 1. And when you do the composition between these elements, of course, we obtain automorphism of omega 1. So you have this corollary. And so we construct like this elements of the Galois group. Then I will need these notations. So if you take an object of this category and we denote like this, the Tanaka subcategory generated by this object, that is the smallest Tanaka category containing this object. And if H is the subgroup of the Galois group, then we denote by HX the image of H in GX. And GX is a Galois group where here we not consider this fiber functor omega 1, but we only consider it on this Tanaka subcategory. And by definition, it is a Galois group. GX is a Galois group of an object of this category. And then to finish, we can prove the following theorem. So we have constructed elements of the Galois group, which is these first matrices. Similarly, we can see that these matrices also are elements of the Galois group. And we can prove that it is sufficient to have a Zariski-dense subgroup in the Galois group of this object. Thank you.
Okay, I'm sorry. Sorry, I had a connection problem. So thank you very much. Are there any questions?
I have a question.
Yep.
Could you explain what happens in the case n equals 1?
So in the case n equals 1, so you have a Mahler equation with a rational function, and then in this case we can compute Galois groups. It is also it is an algebraic subgroup of C star. So it is C star of a group of units of C star, and in this case we can compute it. So in this case, I think for this group here, you will have two possibilities. You have the first possibility is that you have a Zariski-dense subgroup, which is in fact equal to the Galois group in the case of when the Galois group is a finite group. And when you have infinite elements constructed like this, then the Galois group will be all C star. Does it answer your question?
Thank you.
Any other questions for now? Okay, great.
Well,
Then, yeah.
Well,
Please.
I have a question
Oh,
which,
yeah, sure,
which may not be related to the topic here, but so when you have the fixed points at 0 and infinity, in the Mahler case, you said you have to find a matrix on 1. Now, what happens if it is not 0 and infinity? But let's say an A and a Z1 and a Z2.
That means that here, instead of having 0 and infinity
Right.
points where the A is equal to the identity,
Yeah.
and in fact, we have to consider 0 and infinity and not other points, because we have to, we want a solution which is defined on a set table which is stabilized by the operator 50. So it is why we consider fixed point. It is because if you don't consider fixed point of this operator, then you will not have a solution stabilized where domain of definition is stabilized by this operator. So I think that it is why we consider fixed points, but I think that if you consider this condition and maybe you want another condition on these two other points, Z0 and Z1, then you are not anymore in this case. Maybe you can be in the case of a system which is regular zero, but we cannot apply this at two different points, that 0 and infinity, at points which are not fixed by the operator.
Maybe I'll put the question slightly differently. How is 1 related to 0 and infinity in this game?
Okay. In this game, we are considering the point 1, which is also fixed point of this operator. And in fact, when we don't consider this point 1, I don't manage to obtain the Zariski-dense subgroup because we can't consider connection matrices. So in fact, in this game, the point 1 makes the link between the point 0 and the point infinity, because you have the point 0 and you have fundamental matrices defined at this point, which and they have meromorphic coefficients on the unit disk. And then at the point infinity, it is on the complementary of the closed unit disk. So you have this boundary of these two matrices of solution, and we want to make the link between 0 and infinity. You can think of it like that, and the point 1 allows us to make this link. In fact, the point 1 is just here to make the link between 0 and infinity. We have to use it to make this link, because these matrices are defined on disjoint open sets. Okay.
Okay, thank you.
Other questions? Okay, then we can proceed to the breakout room discussion.